Remember that our linear program can be written in standard form, so it's the minimization of C transpose X. We have constraints AX is equal to B, so equality constraints, and we have of course the non-negativity constraint on X. So what we'll do for the moment is forget about the minimization and forget about the non-negativity, and we'll look at this system of equations, right? So we remember that A is an M by N matrix. M is the number of constraints and N is the number of operational variables. And if you write AX is equal to B, well, you see that X is an n-dimensional column vector and that B is therefore AX an m-dimensional column vector. We can assume that the rows of A are linearly independent. This means that A has full row rank and that n is larger or equal to m. The concept of full row rank has been explained in the course Linear Algebra and Applications, so go and have a look if necessary. Let us have a look at what happens if n is smaller than m, right, to illustrate this, and we'll take n is equal to 2 operational variables, m is equal to 3 constraints. So this system of equations looks like this. This is A, 2 columns, 3 rows. X is a column vector with 2 elements, right? And B will be a column vector with 3 elements, right? And since we have 2 columns and 3 rows, we necessarily have here that the rows are linearly dependent. So if we do elimination, we can bring this system of equation to this form, for example. Could be that this second row is also composed of 0, but we'll take this situation. This is still my x vector, and then of course by elimination this vector b here will be different. We'll call it d, and 2 situations can occur. The first situation is that all elements in D are different from 0. But then you can see here from the last equation that this system of equation has no solution, right? And well, if this system of equation has no solution, then the minimization problem does not make any sense, right? The other case is that, well, D could be transformed to something after elimination to something that is like this, okay? Oh, then we have a solution, right? But it also means that we can eliminate one of the equations, okay? So we see here that indeed we can always make the assumption n larger or equal to m, and that the rows of A are linearly independent. If this assumption is not met, this is this case here, this would either lead to contradictory constraints, this is this case, right? Or to redundancy, and then one of the constraints can be eliminated. We have arrived at the conclusion n larger or equal to m, and a matrix A with rows that are linearly independent. This means that A has full row rank. Let us now consider the situation where n is equal to m. Since A has linearly independent rows, well, it means that A has full rank. Okay, so the system of equations ax is equal to b has a unique solution, and by definition it will be also the solution of our optimization problem. So this situation, n is equal to m, does not make much sense. So next, in the next slides, we'll assume that n is larger than m, so the number of operational variables exceeds the number of constraints. So this system of equations has an infinite number of solutions, and n minus m is the number of degrees of freedom left in the optimization problem, and it's larger or equal to 1. Well, we have just seen that we had ax is equal to b and that we could assume n larger than m, right? Let us take an example of that. We'll assume m is equal to 3 and n is equal to 5, right? So we have the following system of equations. So we have in x 5 elements, and this produces here a b with 3 elements, right? So this is a, this is x, and this is b, right? And we have seen that this system of equations, since the lines, so the rows of a are linearly independent, right? Well, this produces an infinite number of solutions. So what we can do here is set in x, well, set n minus m variables to 0. Okay, so what we can do over here is, for instance, set this one to 0 and set this one to 0, right? And this will produce an equivalent system where we can kind of skip this column and the fourth column, and this system of equation where we have fixed x2 to be 0 and x4 to be 0 can be rewritten as, well, the first column of a, the third column of a, and the fifth column of a. And this matrix here, we'll call it the matrix B. And of course, since we have fixed these ones to 0, we can take them out. We'll only have x1, x3, and x5 is equal to b, right? This system of equations has now, well, 3 unknowns, and it has also 3 equations, so it has a solution, right? This type of solution where we fix n minus m variables to 0 and we solve the underlying system bx is equal to b is called a basic solution, right? And the variables that we have selected in this second system of equations are called the basic variables. Here the basic variables are x1, x3, and x5. And since we have assumed n larger than m, well, there will be at least one basic solution. In the previous example, we had ax is equal to b, n larger than m, and we had n is equal to 5 and m is equal to 3, right? And we had kind of fixed x2 to be 0 and x4 to be 0, and this had then led to a system of equations. Bx is equal to b, and if you solve this, well, you obtained x1, x3 and x5, and this then led to a basic solution. And what happens normally is that these ones are different from 0, right? So by looking at the solution and looking at the ones that are different from 0, you can kind of isolate the basic variables. But what can happen is that when you solve this system of equations, right, we have here one of the basic variables that is 0 as well, and this then leads to a degenerate basic solution, right? So in a degenerate basic solution, you have more than n minus m variables that are 0, and it's difficult to know which variable is a basic variable. So far we have left aside the non-negativity constraint, but we remember that in our linear program we have ax is equal to b and x larger or equal to 0, so x is non-negative. So we can then speak about basic solutions still, but if you have a basic solution and all components are non-negative, then we speak of a basic feasible solution, right? Remember that in a basic solution we have n minus m components of x that are 0, right? And here the m components that are non-zero are assumed to be non-negative, right? And if we have a degenerate basic solution, and if it is feasible, this means that all components are larger or equal to 0, then we speak of a degenerate basic feasible solution. Well, of course, we are looking at a linear program, so we have minimization over x of C transpose x with ax is equal to b and x non-negative, right? So this gives you the feasible solutions, and among all the feasible solutions you have the one that minimizes the cost, and this solution is the optimal feasible solution. If this solution turns out to be basic, right, remember that a basic solution is a solution where you have n minus m of the components of x that are 0, well, it is then called an optimal basic feasible solution. Well, let us take an example to illustrate this concept of basic solutions, degenerate basic solutions, and so on. So here we have a system of equations. So for the moment we do not take into account the non-negativity assumption on the components of x. Here we have m is equal to 2 and n is equal to 3, right? So we look at basic solutions. So in this case, well, what we have to do is set n minus m, so one of the components of x to 0. We have, of course, 3 possibilities. We can set x1 to 0, x2 to 0, or x3 to 0, and they will all lead to basic solutions, right? Well, let us take the first case where we set x1 to 0. This is the system of equations. Well, if you set this one to 0, well, you will end up with a system of equation that is this one over here: 1, 1, 2, 0, x2, x3 is equal to 3, 2. This is this system of equations that we had previously. This is the b. This is x, b. It contains the basic variables, and this is b, right? And you can kind of see here that if you set x1 to 0, the second equation will lead to x2 is equal to 1, and if you plug x2 is equal to 1 in the first equation, well, you obtain x3 is equal to 2, right? So you can write this basic solution and find the solution by also writing it like this, right? So this is one basic solution, and as you can see, you have n minus m components of x that are 0. So what you can do, of course, is do something that is very similar and impose x2 is equal to 0, and then you compute x1 and x3, or set x3 is equal to 0 and compute x1 and x2. This will lead to basic solutions, right? Well, you can see here that this third solution leads to x2 is equal to minus 1. So this is a basic solution, but it is not feasible, because what we expect in our linear program is that the components of x are non-negative. So here we have 3 basic solutions, but only the first and the second basic solution will be basic and feasible. And indeed, these are the 2 basic feasible solutions. They correspond to the 2 first solutions in the previous slide. We have changed the example a bit, and we have changed the first element of b. Previously it was 3 and now it is 1, but we still look for, well, basic solution. So what we'll do is impose x1 is equal to 0, right? So we end up with a system of equations where we remove the first column, right? And as you can see here, well, this still imposes x2 is equal to 1. But if you plug x2 is equal to 1 in the first equation, you see that you have x3 is equal to 0. So here in this solution, we have more than n minus m. So n was 3, m is 2, n minus m is 1. So here we have more than one component of x that is 0, and therefore we speak of a basic degenerate solution. And it's difficult to know here, well, which are the variables in the base. Is it x1 and x2 or x2 and x3, right? Of course, there is another basic solution that corresponds to x2 is equal to 0, right? And if you compute the corresponding x1 and x3, this is what you will obtain. So this is a basic degenerate solution, and this is a basic solution. As you can see over here, all components are non-negative, so this will be a basic feasible degenerate solution. In this basic solution, well, the third component here is negative, so this will not be a basic feasible solution. And indeed, among the basic solutions, there is only one that is feasible, and it also turns out to be degenerate, because we have x1 is equal to 0 and x3 is equal to 0. So here we have a basic degenerate feasible solution. Now that we are familiar with the concept of a basic solution and a basic feasible solution, it's time for the fundamental theorem of linear programming. So we're given a linear program in its standard form, and by now this form should be familiar, right? Well, this theorem says that if there is a feasible solution to this linear program, there is also a basic feasible solution. And it says that if there is an optimal feasible solution, then there is also an optimal basic feasible solution. So this theorem tells us that we can restrict our search over all basic feasible solutions. The fundamental theorem of linear programming tells us that it is possible to find an optimal solution by searching over all basic feasible solutions. Well, it's difficult to compute the number of basic feasible solutions because there is this non-negativity, but what we can do is have an idea of how many basic solutions are possible. Remember that we have n variables, m constraints, and for a basic solution we have m of the variables that are different from 0 and n minus m that are equal to 0. So the number of basic solution is sometimes written like this, Cnm. In other references you will see it written like this, but this means the number of m combinations in a set of n elements, and you might have encountered that, you probably have, in a course of probability. So this is n factorial divided by m factorial times n minus m factorials. So this leads to a finite number of basic solutions, right? Of course, if you have to go among all those basic solutions to find an optimal solution, well, this will be rather inefficient, right? Because this number is finite, but of course it can be very high. We'll see in the next section, where we will introduce the simplex method, that it is possible to find an algorithm that will search among all basic feasible solutions, but it will do this in an efficient way. Let us have a look at the proof of the first part of the fundamental theorem of linear programming, and of course this is for your information only. And the idea is that we have to show that if there is a feasible solution, then there is also a basic feasible solution. The interesting case is p larger than m. Then we have a solution x where p of the elements are positive, right? And you can write ax is equal to b as follows. As the number of components, elements in x that is positive is p, and that p is larger than m, this solution x is feasible, right? But it's not a feasible basic solution. So underlying this system of equations we have a matrix. This matrix has m rows, p columns. We'll take an example here where m is equal to 2 and p is equal to 3, right? So there are 3 columns of 2 elements. So obviously these columns, these p columns in here, are linearly dependent, as you can see in this particular example. If the p columns are linearly dependent, it means that you can find a non-trivial means non-zero, linear combinations of these p columns that produces the 0 vector, okay? And this is this linear combination. What we will show next is that at least one of these coefficients here in front in the linear combination is positive. To prove this, what we will do is write B as a linear combination of m of these columns, right? So in this case, for instance, if you take only two of the columns, since the rows are independent, well, you have a base, right? So you can write B in terms of these columns. So in general, what you can do is write B as a linear combination of m of these vectors A, J. And here you have this linear combination. And in this linear combination, well, there are a number of these coefficients here, Zj, that are 0, and they correspond to P minus m coefficients Zj that are 0. This is because we have written B as a combination, a linear combination of m of these columns, right? Well, we had already written B in this fashion over here. This is expressing that X is a feasible solution. So we have two ways to write B. So what you can do is, well, subtract both equations, and then obviously what we'll have is a 0 on the right side, and on the left side we'll have x1 minus z1 times a1 plus etc. Right? We know that these elements here are positive, right? And in this decomposition there are p minus m of the Zj that are 0. So in this decomposition here, in this linear combination that produces 0, right? Well, it's possible to find p minus m elements of this type that will remain positive, right? Because you'll have something positive minus something that is 0. So indeed, it is possible to find a linear combination of the columns here, of these p columns, that produces 0 with at least one element that is positive, at least p minus m even. Well, let us summarize things. We have a feasible solution that meets the constraints. In this feasible solution we have p components that are positive, right? As p is larger than m, we have a feasible solution, but this solution is not basic. We have shown that it's possible to find a non-trivial linear combination of the vectors a1 to ap that produces the 0 vector, and that at least one of the coefficients yj is positive. We'll call this equation 1, this equation 2, and we can therefore construct 1 minus epsilon times the second equation, where epsilon is positive. If the coefficient yj is negative, then a coefficient of this type is going to grow, because you'll have minus minus plus when epsilon is going to be positive. Okay, so the coefficient will grow and it will stay positive. Remember that these coefficients here, x1 to xp, are positive. When one of the yj's is positive, and we know that there is at least one, taking something like x2 minus epsilon y2, and we'll assume here that y2 is positive, will decrease the coefficient when you increase epsilon. And at one stage, if you choose epsilon is equal to x2 divided by y2, well, you'll produce a 0. Okay, you have to pay attention, because maybe there is more than one yj that is positive. So what you'll do is take the first epsilon that makes sure that there is a coefficient that becomes 0 over here, and that's this epsilon. Okay, so that's the minimum of all the xi divided by yi for a yi that is positive. And this value of epsilon will produce a new feasible solution, right? Because it will still meet the equality constraints, but will have a coefficient that is 0, right? So we'll have a feasible solution with p minus 1 positive variables. If p minus 1 corresponds to m, then we have a basic feasible solution. If p minus 1 is still larger than m, we'll have to repeat this process until we find a feasible solution with m positive variables, and this solution is then a basic feasible solution. This completes the proof, and we have shown that when we start from a feasible solution x, it is always possible to find a basic feasible solution. Let us have a look at the second part of the proof, again for your information only. Here we want to show that if there is a feasible optimal solution, then there is also a feasible basic optimal solution. We will assume that we have an optimal solution that has exactly p of the components of x that are positive, right? And the case p smaller or equal to m can be tackled as before. So we'll treat the case p larger than m. Remember that we have found in the first part of the proof a solution x minus epsilon y, right? And we want to show that this solution is still optimal. To do this, we need to compute the associated costs, and this will be C transpose times this quantity over here. And if we compute, this is what we obtain. But for epsilon sufficiently small, this quantity over here, x minus epsilon y, is a feasible solution for positive and negative values of epsilon, as long as epsilon is sufficiently small in absolute value. Okay, so we have to conclude that this thing here is equal to 0. If it were not the case, then we would be able to decrease the cost by appropriately choosing epsilon, but this is not possible because we have assumed that our original solution is optimal, right? So we know that this new solution, this new feasible solution, is also optimal. So if we choose the right epsilon as shown in the first part of the proof, we'll have a solution with p minus 1 components positive that is still optimal. And as in the first part of the proof, we can repeat this until we find a solution that is feasible, basic, and also optimal. And this completes the second part of the proof. Well, in the next few slides, we want to make the link between this concept of a basic variable, and that is a kind of algebraic notion, and we want to make the link with something that is geometric in nature. The geometrical concept that we need is the concept of an extreme point. A point x in a convex set C is an extreme point of C if it is not possible to find 2 points x1 and x2 such that it is possible to express x as a convex combination of these 2 points x1 and x2 for some alpha, with alpha in this interval. So an extreme point is therefore a point that does not lie on a segment that connects two other points of the set. So for instance, an extreme point of a triangle are the vertices. So if we draw a triangle. For instance, for this point over here, it is possible to find 2 points x1 and x2, and it is possible to express x here as a convex combination of x1 and x2. And it's obviously also true, for example, for an x that is over here. But for an x that is on the vertices, right, it is impossible to find 2 different points, of course, such that these points can be expressed as a convex combination of 2 different points, x1 and x2. So here we can link the notion of a basic feasible solution and an extreme point. Remember that in our linear program we have, well, a feasible set that can be expressed as follows. It's the solution of a matrix equation with elements in X that are all non-negative, and we had said that, well, this feasible set is a convex polytope, right? This difficult name, but remember that for n is equal to 2, then we have a polygon, right? And for n is equal to 3, we had this polyhedron, right? So polytope is kind of a generalization to an n that is larger than 3. And we can show, it is possible to show, we won't do it, that a vector x that is an extreme point of k corresponds to an x that is a basic feasible solution. We have seen from the fundamental theorem of linear programming that we have to look for an optimal solution among all basic feasible solutions. This is an algebraic interpretation. The geometrical interpretation is that an optimal solution can be found in a vertex of the feasible set. What you're seeing here is a representation that comes from the Wikipedia page on the simplex algorithm. The feasible set that is shown here is in general a convex polytope, but for n is equal to 3, and this is what is shown here, it becomes a polyhedron. The simplex algorithm that will be introduced in the next section provides a systematic way to go from one vertex to another, from one extreme point to another, while decreasing the cost. And the path is shown here in red. Note that the simplex algorithm that will be introduced in the next section will run systematically over all basic feasible solutions, or equivalently over extreme points or vertices. So in this particular case here, it will either find this optimal solution that is on a vertex, or this optimal solution that is on a vertex. It will all depend on the method that is used and the starting points and things like that. It will not be able to identify that in this case there are an infinite amount of solutions that are on the ridge of this feasible set. Note that this situation here, where we have an infinite amount of solutions, is uncommon, and in any way, in most cases, we are happy to find just one optimal solution, and in this case it will be a basic feasible solution or a vertex of the feasible set. We'll now use an example to show this equivalence between a basic feasible solution, which is an algebraic notion, and, well, an extreme point or a vertex, which is a geometrical notion. So we'll work in r square so that we can represent things, right? And there are 3 constraints here, and since we work with, well, non-negative x1 and x2, we only have to consider r square plus. Since we work in R square with 2 operational variables, we can represent everything. So we have the 3 constraints and the non-negativity constraints on x1 and x2, and this generates a feasible set, and this is now this convex polytope. But since n is equal to 2, this generates a convex polygon, right? And if we have a look, indeed there are a number of extreme points or vertices, and in this case there are 5, and they are shown over here. Well, to introduce the basic feasible solutions, we'll have to go to the standard form and take this set of constraints where you have inequalities smaller or equal than, and transform them in 3 constraints where you have equalities, and for that you'll have to introduce a slack variable in each of the inequalities. So this will produce 3 equations with 5 unknowns, 2 operational variables and 3 slack variables. And indeed this is what we obtain: 3 equations, 5 variables, and a basic solution is obtained by setting n minus m, that is n is equal to 5 minus m is equal to 3, 2 variables to 0. So what you see over here is this feasible set that is in R5 plus, that is projected on the plane x1, x2, and what you see over here is, as before, x1 is equal to 0 and x2 is equal to 0, and notice that x3 is equal to 0 corresponds to, if x3 is equal to 0, well, x3 is equal to 0 corresponds to x1 plus 8/3 of x2 is equal to 4, right? So this is what we had in the previous representation of the feasible set. So this extreme point corresponds to a basic feasible solution where x1 is equal to 0 and x3 is equal to 0, and the other components of x are different from 0. And you can do something similar for the other extreme points. They all correspond to a given basic feasible solution. So we'll now minimize an objective function subject to the constraints that we had considered before. Notice that these constraints are not expressed in the standard form, but we'll still be able to consider the extreme points of the feasible set as candidates for the optimal solution. And indeed, if we consider lines of this type over here, and we draw them on the feasible set, we can see that the line that corresponds to the optimal solution is this one over here. The minimal cost is minus 3.5 and the optimal solution is this one, and indeed it is an extreme point of the feasible set, and in this case the feasible set, which in general is a convex polytope, or this feasible set in this case is a convex polygon again. So here's the example well solved with Matlab code. The first part of the code is not that interesting, it's just to produce the feasible set, and the second part of the code is used to solve the linear program. And as you can see here, there is a function in Matlab, linprog, that allows you to solve linear programs. Let us have a look at the help for linprog and to solve linear programming problems. As you can see, the best thing is to go to the reference page. This is what you obtain, and as you can see, you can use this function to solve linear programming problems with a linear objective, of course, but you can handle inequalities, smaller or equal. If you have inequalities larger than equal, you'll have to multiply your equation by -1, and you can combine with equality constraints, and you can even put bounds on x, right? In our case, we have transformed such problems in a standard form where we only consider equality constraints and bounds of the type non-negative, right? But if you have a problem, you can solve it in Matlab without having to bring it to this standard form. You can see that there are several algorithms that you can use. You can choose the simplex method that we'll introduce in the next section, and you can also use the interior point algorithm. That's the default. This is this algorithm that I've mentioned in the introductory course, although it goes beyond the scope of this course. So here you recognize the objective function, right? Here the three inequality constraints, and here the two non-negativity constraints on the two operational variables x1 and x2. And as you can see here, well, the simplex algorithm has been set. And indeed, if we run the code, this is what we obtain with the optimal solution as shown in the slide. In the next subsection, we consider duality. So when we have a linear programming problem, we can consider a dual problem, the original problem being the primal problem. Well, to illustrate this, we'll use the problem that we had considered previously, the problem of the most economical diet. Well, there are n different foods available on the market, with j running from 1 to n, and each food comes at a price Cj per unit. And we need to determine xj, the number of units of food j in the diet, and for that we'll minimize the total costs, and the total cost is, well, c transpose x, that is c1 x1 plus c2 x2 up to cn xn. There are of course constraints, and the constraints come from the fact that there are m different basic nutrients, right? And here we use the index I that runs from 1 to m, and to achieve a balanced diet, an individual must receive at least bi units of the nutrient I per day. Each unit of food j contains aij units of nutrient I. So for each nutrient I, we have to ensure that the diet gives you a supply of the nutrient that is higher than what each individual must receive per day, and this imposes m constraints, and they are of this type over here. And of course we have non-negativity constraints on the xj. Well, the dual problem can be thought of as follows. Imagine that you have a pharmaceutical company that produces the m different basic nutritional ingredients, so the nutrients, proteins, lipids, imagine that it's vitamins for instance, in pill form. Okay, and the company of course must set unit prices, and we'll call them lambda I for the pills, and the lambda I here will be the operational variables, and there will be I ranging from 1 to m prices to set, because there are m nutrients. And of course a company wants to maximize the revenue, and this revenue, well, depends on the unit prices and the individual needs of the people in the form of these nutrients in pills, right? So in the dual problem we'll have a maximization problem. And where do the constraints come from? Well, to be competitive with the actual food, right? Because of course an individual can get the nutrients from real food or from the pills. The cost of an artificial unit of food J made from pure nutrients in pill form must be not greater than Cj, the price of this food on the market, right? So this produces J constraints, because there are J types of food, and now we have constraints that are of the type smaller or equal, right? Whereas before we had constraints larger or equal. So in the primal problem we have a minimization, right? And the constraints are of the type here larger or equal, right? Here we have n operational variables and we have m constraints, right? In the dual problem we have a maximization problem, and the inequalities are smaller or equal constraints, right? And we have m operational variables and n constraints. As you notice here, the primal problem and dual problem have been written in terms of vector and matrix notations. Note that duality is not something that we want to focus on in this 15-hour course, and it will not be a topic at the exam. We will see later that the solution of the primal problem and the dual problem are somehow linked.